Hello, our today's question is the correct statement among 1, 2, 3 are. First statement is valence bond theory cannot explain the color exhibited by transition metal complexes. Second statement is valence bond theory can predict quantitatively the magnetic properties of transition metal complex. And the third is valence bond theory cannot distinguish ligand as weak and strong field ones. And we have given the options. So let's try to understand this question. So first of all, we should know that color of complex depends upon electronic transition made in d orbital. Therefore, but the valence bond theory, that is VVT, does not give doesn't give any idea about the color in a substance, and it is given by CFT, that is crystal field theory, CFT. And therefore the first statement is correct. Now the second statement is basically the magnetic property. So magnetic property of metal can be predicted by number of unpaired electron present by filling of electron in orbital. The VVT, however, the VVT, valence bond theory, does not give quantitative behavior it gives only qualitative nature. Therefore second statement is wrong. Now third statement is based on strong field and weak field legend. So strong field legend SFL and weak field legend WFL is determined using spectrochemical series. Spectrochemical that was prepared experimentally, and VVT has nothing to do with any such series. Therefore A and C are correct option and B is not correct. Now if we look at the option, so 1 and 3 are correct. Therefore option C will be our final answer. Hope you understand. Thank you for watching the video.
Hello. So question says that the correct statement about the ICL5, right? So we have to compound ICL5 and ICL4 negative, right? So just we have to tell that which of this following statement is correct about regarding this X, or you can say regarding this compound, right? So let's try to solve it, right? So compound 1 is here ICL5, right? So compound 1 is ICL5, right? So this is ICl5 and the compound second, right? So we have two compound, that is, you can say that ICl5 and it is an interhalogen compound, right? And similar here is ICl4 negative, right? So ICl4 negative, right? So these are the two compound, right? So just before solving this question, we have to understand a basic concept, that is the concept of steric number, right? So we know that steric number is used for calculating the hybridization and, or you can say, geometry of the particular compound, right? So this is our steric number, right? And this is our hybridization, right? Hybridization, and this is our geometry, right? So I can say this is a geometry, right? Right. So this is geometry. I can say this: the if the steric number is 2, then the shape will be SP. Not shape, it is hybridization will be SP, and shape will be, geometry will be linear, right? Geometry will be linear, right? And if the steric number comes out to be 3, then hybridization will be SP2, and the geometry will be trigonal planar, right? So it is trigonal planar, right? And it is trigonal planar. And if the steric number comes out to be 4, then the hybridization will be SP3, and shape will be, not shape, it the geometry will be tetrahedral. And the steric number comes out to be 5, then hybridization will be sp3d, and geometry will be trigonal bipyramidal, right? Trigonal bipyramidal, right? And if the steric number comes out to be 6, then hybridization will be sp3d2, and geometry will be octahedral, right? So this is the basic concept regarding the, just for finding out the hybridization or geometry of that particular compound, right? So by using this concept of steric number, right? So we have to just understand that how we'll find out the steric number, right? So this is a simple formula for calculating the steric number, that is number of lone pair, right? So it is number of lone pair, right? Plus number of bond pair, right? Number of lone pair plus number of bond pair. So just we have to add the bond pair and lone pair, and we will get the steric number, right? Say for example, we have a compound ICl5, right? So we have a compound ICl5, and for this compound, that is ICl5, right? So this is compound our ICl5, which is an interhalogen compound, right? So which is an interhalogen compound. So let's try to find out the lone pair and bond pair, right? So we know that in the case of iodine, there are 7 valence electrons, right? So there are the 7 valence electrons: 1, 2, 3, 4, 5, 6, and 7 valence electrons, right? And here the chlorine is attached. That means the chlorine is bonded by the iodine is through single bond, right? So I can write here chlorine is bonded through single bond. So one chlorine here. So this is one chlorine, and this is second, and this is third, and this is fourth, and this is fifth, right? So there are 5 chlorine, and this the remaining electrons are acting as a lone pair, right? So I can write here as there is one lone pair, right? So here we get one lone pair, right? We get one lone pair plus 5 bond pair, right? So one lone pair plus 5 bond pair, right? So 5 bond pair are of chlorine, right? So this is 1, 2, 3, 4, 5. These are the 5 bond pair, right? So if I add it, the I will get 6, right? And 6 implies that the hybridization will be sp3d2, right? So hybridization will be sp3d2, and the geometry will be octahedral. But this does not about the shape, right? So in shape we do not count the lone pair, right? So in shape we do not count the lone pair, right? So remember it. So let's try to find out the shape of this ICl5 compound, right? So if I draw the structure, or you can say in case of iodine, then we have octahedral geometry like this. This is the octahedral geometry, right? So if I, you can say that this is iodine. If I draw the geometry like this is octahedral geometry, and if I connect it through a chlorine, right? So this, there is one chlorine here, and there is one chlorine here, right? And one chlorine here, one chlorine here, and one chlorine here, right? So there are 5 chlorine, and the remaining lone pair exists like here, right? So this is lone pair, right? So if I draw it clearly, so it becomes a lone pair, right? Lone pair. So right, look like this, right? So it is kind of square pyramidal type structure, right? So if I connect it like this, so it becomes a square pyramid, right? So this is a square, right? So it looks like a rectangle, but it is actually square, right? Because all bond angles are 90 degree, right? So if I connect it through this, so it becomes a pyramidal type structure, right? So you can look there. So we get a shape of square pyramidal here, right? Square pyramidal, right? This is square pyramidal, right? So now if I see the another compound that is ICl4 negative, right? So if I see the another compound that is this compound number second, that is ICl4 negative, right? ICl4 negative, right? So negative means we have to just add a one electron, right? So similar process applies here. In case of iodine, there are 1, 2, 3, 4, 5, 6, and 7 valence electron, right? So we have a negative charge here. So we just add another electron, that is 8 electron, right? So we have to add a 4 chlorine, right? So we have to add 4 chlorine. That means we can write here as 1 chlorine here, 1 chlorine here, 1 chlorine here, and 1 chlorine here, right? So there are 4 bond pair, and the remaining 2 electrons are, there's 1 lone pair here and 1 lone pair here, right? So we will get 2 lone pair, we'll get 2 lone pair plus 4 bond pair, right? So we will get 2 lone pair plus 4 bond pair. So it implies that the steady number comes out to be 6. It implies that the hybridization will be sp3d2, right? And geometry will be octahedral, right? So geometry will be octahedral, right? So this will be the geometry will be the octahedral, right? So in this case, the geometry will be look like this, right? So this is iodine, and geometry will be look like this, right? This is geometry, right? So and all the chlorines are arranged like this. All the chlorines are arranged like this, right? So this is chlorine here, and this is chlorine here, and these are the 2 lone pair, right? So these are the 2 lone pair, right? So and the shape will be look like this. That is square, and all the chlorine are in plane, right? So I can say that the shape of this compound is square plane, right? So the shape of this compound is square plane, right? So here I can see this. The compound of ICl4 negative has a square shape, and the ICl5 has a square pyramidal shape, right? So ICl5 has a square pyramidal shape, right? So ICl5 has a square pyramidal shape, and ICl4 negative has a square planar shape, right? So let's see the option. And options are, let's see the option. And option says that, if I see the option, then option says this: both are isostructural, right? So and both are isostructural, right? So because this statement is wrong, right? So this option is wrong, because isostructural are those spaces which have same structure, right? So but we have seen that ICl4 has a square pyramidal structure, and ICl4 negative has a square planar structure, right? So they are not isostructural, right? And ICl5 is a trigonal bipyramidal geometry, right? So and ICl4 is tetrahedral, right? So but we know that ICl4 negative is square planar, it is not tetrahedral, right? So I can neglect it, right? So I, in this case, the option B will be the wrong answer, right? And in here ICl5 is a square pyramidal, right? So this is the correct statement, but ICl4 is here tetrahedral, but we have a square planar, right? So this statement is also wrong, right? So I can say that option C will be the wrong answer. So here option D says that ICl5 is a square pyramidal and ICl4 negative is square planar, right? So this statement seems to be correct, right? So this is our correct answer, right? So here our correct answer will be ICl5 is a square pyramidal and ICl4 negative is a square planar, right? So we are left only with the correct answer, that is option D. So which has a ICl5 has a square pyramidal structure and ICl4 negative has a square planar shape, right? So this is the answer, right? So hope this answered your question. So thank you.